Okay, acid-base titration calculation. We'll start with strong acid, strong base titration, in which you're asked to titrate 20 milliliter sample of 0.10 molar hydrochloric acid with 0.10 molar sodium hydroxide. This is shown in an illustration here. 0.1 molar sodium hydroxide is added to a burette, and portions are added to the 0.1 molar hydrochloric acid until we reach the equivalence point, and anything after the equivalence point is surplus base. The titration curve generated will have a pH at the of equivalence point equal to 7, because the salt from strong titrations does not, the ions from the salt do not hydrate. Here's an example of the titration curve of a strong acid and a strong base titration, in which the base is added into the hydrochloric acid and the change in pH is monitored relative to the acid. We begin the calculations with a general estimation of how much base will be required to reach the equivalence point. This is done so that you can plan the amounts to be added, and you'll have an idea of where to reduce the number of milliliters of added base as you approach the equivalence point. Notice how it's very narrow volume of base results in very quick increases in pH and small amounts of sodium hydroxide. So you want to know or estimate how much base is going to be used to reach the equivalence point. So the first thing we do is estimate volume of NaOH needed to neutralize 20 milliliters of 0.10 molar hydrochloric acid solution. Right there. Well, basically, and we're assuming the concentration of NaOH is 0.1 molar, sorry, not 0.01, 0.1 molar. Okay, so we know that molarity times the volume of the acid is equal to molarity times volume of the base. And we're interested in determining how much base we're going to be using to reach the equivalence point. So the volume of base is equal to molarity times volume of the acid divided by the molarity of the base that you are going to use. So the molarity of the acid is 0.10 molar, and if you have 20 milliliters divided by 0.10 molar base, molarities drop out, then you're going to need 20 milliliters of 0.10 molar sodium hydroxide. So the point being, as you approach the 20 milliliter marker, volume of equivalence point equals 20 milliliters, that's your theoretical, then say in the 15 mil range, you'd probably want to reduce the amount added to maybe half mil quantities in order to obtain a number of points in the inflection area. Okay, to start the calculations, we calculate the pH after adding specified quantities of base into 20 milliliters of 0.1 molar HCl. The essence of a titration problem, it is a limiting reagent problem until you reach the equivalence point, with the limiting reagent being the sodium hydroxide in this case. will be consumed, and we'll have an excess of hydrochloric acid, but that excess will decrease until we reach the equivalence point. So we'll start with 5 milliliter addition of 0.1 molar sodium hydroxide. Well, you need to convert that to moles in the following way. Molarity times volume in liters will give you moles of sodium hydroxide. Now, we know that sodium hydroxide plus hydrochloric acid is a 1-to-1 reaction ratio to produce sodium chloride plus H2O. So we want the number of moles of sodium hydroxide. That'll be 0.005 times 0.10 mole of sodium hydroxide, and that's added into 0.02 times 0.10 mole of hydrochloric acid solution. So now that gives me 0.0005 mole of sodium hydroxide plus 0.0020 mole of HCl. Now the remaining HCl, that is excess, after neutralization, is equal to 0.0020 minus 0.0005. And so that gives us 0.0015 mole of HCl remaining. This needs to be converted to concentration terms and molarity. So if we have this, then the concentration of HCl, which is concentration of the hydronium ion, because the hydrochloric acid will ionize 100%, is equal to moles over the combined volume in our reaction, is 0.0015 mole of HCl, and that's 25 milliliters of 0.025. So this gives us 0.06 molar in hydrochloric acid, which is also, of course, 0.06 molar in hydronium ions. So to calculate the pH of the solution after we add the first 5 mils of sodium hydroxide is minus log of the hydronium ion concentration, which is minus log of 0.06, which is the hydronium, and that gives us 1.22 is the pH after the first 5 mils of 0.1 molar sodium hydroxide is added into the solution. Now we will look at adding another 5 mils, if you will, of sodium hydroxide solution, 0.1 solution, into a 20 mil sample of hydrochloric acid. Now the next calculation is like starting all over again. We'll list right here, instead of 5 mils, we'll put 10 mils of 0.1 reacting with 20 mils of 0.1 HCl. And this is what we'll show. So now we want to calculate what the effect of 10 mils of 0.1 sodium hydroxide addition will have on the 20 mils of 0.1 molar hydrochloric acid. And again, we'll start with calculating moles and apply it to the reaction ratio, which is 1-to-1. Subtract out the amount of acid that's been neutralized, and that'll be the remaining. Convert to molarity and recalculate the new pH. So it goes something like this. We'll use 0.010 times 0.10 mole sodium hydroxide is now reacting with 0.02 times 0.10 mole of hydrochloric acid, and this of course gives us 0.0010 mole sodium hydroxide reacting with 0.002 mole of hydrochloric acid. Well, this is only going to take out 0.001 mole of the HCl, so we're going to have 0.001 mole of HCl remaining, because this will neutralize only 0.001 mole of the acid. So it would subtract 0.0020 minus 0.0010. This represents the amount of acid neutralized. And so we would have 0.0010 mole of HCl remaining in excess. Now, of course, there is there's also 0.001 mole of sodium chloride floating around in the solution, also from the neutralization reaction. Well, we need to calculate the new concentration after the, say, 2, which would be hydronium ion after the second titration, and that is 0.0010 mole of HCl divided by 10 and 20, that's 30, 0.030 liters. So that will convert to 0.0033 molar in hydrochloric acid, which is also 0.033 molar in hydronium ions. Now we'll take the hydronium ions and apply it to the pH equation. pH after the second titration, say, is minus log of the hydronium ion concentration at the second titration, 0.033, and that takes us to 1.48. The pH after addition of 10 milliliters into 20 milliliters. Now then, for the next calculation and the titration sequence, we'll bump up the base addition to 19 milliliters of 0.1 molar sodium hydroxide and its effect on 20 milliliters of 0.10 molar HCl. Now we'll have 39 milliliters total, so we can divide by 0.039, convert the moles back to molarity. So in this one, we have 0.019 times 0.10 mole sodium hydroxide plus 0.02 times 0.10 mole hydrochloric acid. So now we have 0.0019 mole of sodium hydroxide mixed with 0.002 moles of hydrochloric acid. So the 0.0019 mole of sodium hydroxide will neutralize 0.0019 mole of the hydrochloric acid, and we'll have a little bit in excess. That is 0.0020 minus 0.0019 mole HCl excess. So that leaves us 0.0001 mole of HCl excess, which is also 1 times 10 to the minus 4 mole of hydronium ions in excess. Right there. So now converting this to molarity, we find 1 times 10 to the minus 4 mole of hydronium ions in 39, 20 plus 19, 39 milliliters converted to liters will give us 2.56 times 10 to the minus 3 molar in hydronium ions now. So from that we can get the pH after the third titration, which is minus log of 2.56 times 10 to the minus 3, and we have 2.59. It's still quite a ways from the equivalence point of 7 for a strong titration. So even though looks like we're right on top of it, 19 milliliters, it's changing, still is below the equivalence point. So to illustrate how the pH approaches the equivalence point, we'll take a look at 19.99 milliliters of sodium hydroxide, 0.1 molar, into 20 milliliters of 0.10 molar hydrochloric acid. So this is the setup for that titration. So we're adding 19.99 milliliters of the 0.10 molar sodium hydroxide into the 20 milliliters of 0.1 molar. So molarity times volume in liters gives us 0.001999 mole of sodium hydroxide reacting with 0.00 or mixed in with 0.0020 mole of hydrochloric. So we calculate the remaining hydrochloric acid in the same way we've been doing, because only 0.001999 mole of the hydrochloric acid will be neutralized, and then we'll have a little bit of excess, so that's 0.0020 minus 0.001999 mole of HCl remains in excess. So that would give us 1 times 10 to the minus 6 mole of HCl remaining after that addition. So converting to molarity, as we have in the last titrations, we divide by 20, 39.99 milliliters, or convert to liters. So there we have 2.5 times 10 to the minus 5 molar and hydronium ions, which would give us a pH after the fourth titration and 4.6. So we're still not at the equivalence point, but you can keep stringing out nines on the amounts added, 19.999999. It will get fairly close to the 7 point. So we're going ahead and hit the equivalence point with titration number 5 being 20 milliliters of 0.10 molar sodium hydroxide plus 20 milliliters of 0.10 molar hydrochloric acid, like this. Well, because of the sodium hydroxide reacting in a 1-to-1 with HCl to use sodium chloride plus water, we find that 20 milliliters of 0.1 is 0.002 mole of sodium hydroxide reacting with 0.002 mole of hydrochloric acid to yield 0.002 mole of sodium chloride and water. And so this is what we would end up with at the equivalence point. Now, if we tested each of the ions, well, if you had to calculate it in concentration moles per liter terms, it'd be 0.0020 divided by 40 milliliters, or 0.040 liters, which leaves us with about 0.05 molar in sodium chloride. Now, at the equivalence point, does this particular salt have any effect on the pH due to hydrolysis effect? See, sodium chloride, being a salt, will ionize 100% of sodium plus chlorides. If we react sodium with water, we'd get, theoretically, sodium hydroxide. Well, sodium hydroxide is a strong base. So if it produces a strong electrolyte, then we say no reaction occurs. So now we look at chloride in water. So if we take chlorine and react it with water, we get hydrochloric acid. Well, that's a strong electrolyte, so we say no reaction. So the pH at the equivalence point after titration 5 of a strong acid plus strong base depends only upon autoionization of water. Here, as you recall, at 25 degrees Celsius, it's been reported that water will ionize to hydronium ions and hydroxide ions such that each one is in an amount of 10 to the minus 7 molar. So calculating the pH at the equivalence point of the hydronium ion, we have minus log of 10 to the minus 7, which gives us a pH of 7 at the equivalence point of a strong acid, strong base titration. Addition of any more sodium hydroxide only functions to increase the pH, and sodium hydroxide is in excess because it doesn't have anything to react with past the equivalence point. Okay, now we want to look at the titration of a weak acid using a strong base. And this is set up in the same way that you set up the strong. Now, in this titration, you'll find adding the sodium hydroxide to a 0.1 molar acetic acid solution, 20 milliliters. We'll follow a titration trend, not to scale obviously, but you'll find the pH at the equivalence point will be greater than 7, because watch for the anion of the weak acid, once it's formed into a salt, will turn around and react with the water and leave the system with an excess of hydroxide. So as we go through this titration, we will have to take into account at the equivalence point the hydrolysis of the acetate ion and its effect on the pH due to hydrolysis. Okay, so now we'll follow the same pattern that we followed in the strong titration. We'll start with 5 mils, go to 10, and then say 29 point or 19.999 and so forth. Do the same routine. But the one thing that you have to take into account in this type of titration is that it's a common ion effect. It also has to be taken into account for determining the equivalence point, the pH as you titrate the weak acid. Okay, just as we did in the strong titration, we will determine the theoretical volume of base required to reach the equivalence point of 20 milliliters of 0.1 molar hydrochloric acid. This again is just a simple calculation, neutralization equation. Molarity times volume of the acid is equal to molarity times volume of the base. And so we solve for volume of the base. Theoretically required is molarity times volume of the acid divided by the molarity of the base. And so very quickly we can get 0.10 molar times the volume. We're using 20 milliliters divided by the molarity of the base, also 0.10 molar. So this cancels very quickly, and we find that the theoretical amount of base needed is 20 milliliters. So we can plan our titration accordingly as we go through and approach the equivalence point. Okay, now for the first titration, of course, we have to determine the pH before the titration begins. So acetic acid solution, and we've got 20 milliliters of it. Okay, so it doesn't matter how much you've got, but we want to determine the pH of a 0.1 molar acetic acid solution. Now I have to give you the Ka value here to be 1.8 times 10 to the minus 5, like that. Now it can be shown that for a weak acid in pure water, the hydronium ion concentration is the square root of Ka times the weak acid concentration, like that. And so we have 1.8 times 10 to the minus 5 times 0.10 molar solution, and it'll come out in moles per liter. So the concentration of hydronium ion is 0.00134 or 13 molar in hydronium ions. So now we can calculate the pH. This is the original or the initial pH minus log of the hydronium ion concentration of the weak acid in solution, which is minus log of 0.0013 molar, and that gives us 2.89. That's before we add any sodium hydroxide solution into our titration. Okay, now to begin our titration, we'll add 5 milliliters of 0.1 molar sodium hydroxide into 20 milliliters of 0.1 molar acetic acid. Now, you have to take into account not only the change in concentration of the acetic acid, but also the production of the conjugate base acetate ion, because that will have a direct common ion effect on the outcome in the pH. So we need to take a look at what the equilibrium equation looks like, because as you neutralize the acetic acid, you're going to be producing some acetate ions, and that has to be taken into account in terms of a common ion effect. So we have to apply those concepts. So I'll show you 0.005 times 0.10 molar leaves us with adding so many moles of sodium hydroxide into 0.02 times 0.10 mole of acetic acid. So this works out to be 0.0005 mole sodium hydroxide added and 0.0020 mole of acetic acid. Okay. Now the excess sodium acetic acid is equal to 0.0020 minus 0.0005 mole of the HOAC. So this gives us 0.0015 mole acetic acid in excess, and we need to convert that excess to moles per liter, so that'd be 0.0015 mole of acetic acid and 25 milliliters, which is 0.025 liters. And we find that this is 0.06 molar in acetic acid remaining after the first 5 mils of strong base is added. Now, we also have to take into account the formation of the salt, sodium acetate, and the presence of the acetate ion, because it functions as a common ion. And so we have to take those concepts into account. So we ask ourselves, well, what is the concentration of the acetate ion after we add so much of the base to neutralize? Well, the amount of salt produced is equal to the amount of acid neutralized, and the amount of acid neutralized is the amount of base added. So you might make a note here, the amount of salt produced equals the amount of base added. So if I add 0.0005 mole of sodium hydroxide, I'm going to neutralize 0.0005 mole of acetic acid, and that's going to produce 0.0005 mole of acetate ions. So we find that the moles of OAC now is equal to 0.0005 mole. Okay, and the concentration of the acetate ion now is equal to 0.0005 mole over the 25 milliliters, 0.025 liters, giving 0.02 molar in acetate ions, along with the 0.06 molar acetic acid. So in order to now determine the hydronium ion concentration, we have to apply concentration of acetate ions and the concentration of acetic acid to the acetic acid equilibrium. So at this point we write the acetic acid equilibrium and note that at initially it has these concentrations. Here's the acetic acid, here's the acetate ion, so we have 0.06 molar here and 0.02 molar right there. And in the common ion concept, we assume this is 0. To start with, it's so small it goes out very quickly. The change in concentration, this of course will go down by X. This was up by X is what we're looking for, and this will also increase by X. And at equivalence point, we have 0.06 minus X, and 0.02 plus whatever X is. Well, X is going to be in the order of 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. So that's a very, very small number. So we can drop X without experiencing any error. So we can just approximate this at 0.06 molar and approximate this at 0.02 molar in those ions. So now we apply this data to the equilibrium expression for acetic acid here and solve for the hydronium ion concentration, and then calculate the pH once we determine what that is. So that is Ka times acetic acid concentration divided by the conjugate base concentration, acetate ion. And so we bring that down here to the hydronium ion now is 1.8 times 10 to the minus 5 for the Ka for acetic acid, and the acetate is 0.06 molar, and that's divided by the acetate ion, 0.02 molar, drops out, and we'll find the hydronium ion concentration now is 5.4 times 10 to the minus 5 mole per liter in hydronium ions, and that leads us to a pH. I hate to get it off the page, but now the pH after the first titration, 5 mils, is minus log of the hydronium ion concentration as usual, and minus log of 5.4 times 10 to the minus 5, and we get a 4.26. So we're now increasing the pH. So the original pH before the titration began was 2.89. Now after adding 5 milliliters of the 0.1 molar sodium hydroxide, now we've jumped from 2.89 to 4.26. So now we want to make another calculation, a second calculation in the titration, where we'll add, say, 15 milliliters. We can do 10, 15. We'll go to 15 milliliters this time instead of just 10. And see. Okay, so here we have 15 milliliters of 0.1 molar sodium hydroxide added into 20 milliliters of 0.1 molar HOAC. And again, we convert to moles and see how much of the acetic acid is neutralized and how much of the acetate ions produced, and apply it to the equilibrium expression of HOAC and determine the hydronium ion as we did in the last example. So here we find is 0.015 times 0.10 mole sodium hydroxide plus 0.02 times 0.10 mole of acetic acid. Molarity times volume in liters. We have to convert, of course, the volume 15. That's where that number comes from. Molarity times volume gives us. So this computes to be 0.0015 mole of sodium hydroxide added into 0.0020 mole of acetic acid. So we will neutralize 0.0015 mole of the acetic acid, leaving some excess acetic acid, and we can calculate that as 0.0020 minus 0.0015 mole HOAC in excess, which of course is equal to 0.0005 mole acetic acid excess, which leaves us with now a concentration of acetic acid after the third titration to be 0.0005 mole, and now we're in 35 milliliters solution, 0.035 liter, 0.014 molar in acetic acid. Now, of course, the amount of salt, the acetate, in the equilibrium equation, we added 0.0015 mole of sodium hydroxide. That means we're going to produce 0.0015 mole of acetate ion, and so the acetate ion concentration now is 0.0015 mole formed when we added that much base, and it too is in 0.035 liters of solution. And that gives us a 0.043 molar in the acetate ion. So now that is applied to the equilibrium expression for acetic acid, and then calculate the hydronium ion concentration. So here I'm just going to make these two at equilibrium. So our concentration at equilibrium is now 0.014 molar, and here we're looking for the hydronium ion, so 0.043 molar in the acetate ion. So the hydronium ion concentration, of course, is Ka times HOAC divided by the acetate concentration, which is 1.8 times 10 to the minus 5, times HOAC concentration is 0.014 molar divided by 0.043 molar. This will all come out in moles per liter, and that gives us 5.86 times 10 to the minus 6 moles per liter, and put a molar in there, hydronium ion, and we take the logarithm of that. We have a 5.23 pH. Squeeze this in down here. So now the pH is equal to minus log 5.86 times 10 to the minus 6, which is equal to 5.23. So now we're climbing up the titration curve, starting from 2.89 to 4.26. Now we're at 5.23. Now you can continue with other increments short of 20 milliliters of base, and you will begin to converge on the equivalence point. At this point, I'm going to jump to the equivalence point and make the equivalence point pH calculation, and show you that, and we'll finish this activity, this lecture. So now we were looking to calculate the pH at the equivalence point for 20 milliliters of 0.1 molar sodium hydroxide added into 20 milliliters of 0.1 molar acetic acid. Now we can set this up as follows. You take 20 milliliters of 0.10 molar sodium hydroxide plus 20 milliliters of 0.10 molar HOAC will of course give you 0.002 mole of sodium hydroxide plus 0.002 mole of acetic acid. Now that's equal mole amounts. Now since the HOAC plus sodium hydroxide reaction completely neutralizes at 1-to-1 mole ratio, reaction ratios, and we have sodium acetate and H2O. So we 0.002 mole of acetic acid and 0.002 mole of the sodium hydroxide produces 0.002 mole of sodium acetate. Now, at the equivalence point, you need to understand that there's really no acid there, no base there, originally. The addition of the 0.002 mole of sodium hydroxide completely neutralizes the 0.002 mole of acetic acid, forming 0.002 mole sodium acetate. So at equivalence point, only 0.0020 mole sodium acetate remains. And from that we can determine the pH of the effect from the acetate. Now, sodium acetate is a salt and ionizes 100% to sodium ions and acetate ions. And so the procedure is to check each of the ions theoretically with the water, reacting with water, and we know that sodium reacting with water will produce no reaction because sodium and water would theoretically generate sodium hydroxide, which is a strong base. And so we surmise that no reactions occurring from the interaction of sodium ions and water. However, the acetate ion is a reasonably strong conjugate base when reacting with water, produces some acetic acid plus an excess of hydroxide ions in the process. Now, starting with initially with 0.002 mole, we need to get that in concentration terms of moles per liter, molarity. So that's 0.002 mole is now in 40 milliliters or 0.04 liters, and that equals 0.05 molar in the acetate ions. Now at the equivalence point, this reacts with water and we'll go at equilibrium. This reaction produce equal amounts of acetic acid and hydroxide. Now if we can determine the hydroxide concentration or X, and from this, then we can get the pH. We can get pOH and of course pH. So we'll scoot down to this position. Let's see. What we're looking for is I call it the KB prime for the conjugate base. Well, that's not published, and so but it is calculated from the expression Ka times Kb equals Kw, so that is Kw over Ka. Ka for the acetic acid, and I write it up here, KaHOAC is equal to 1.8 times 10 to the minus 5, and we'll use that in this expression shortly. Now this equilibrium expression is acetic acid concentration times OH generated divided by the acetate, which is the salt amount generated. So this acetic acid and hydroxide are X, so that's X squared over the acetate salt produced and the reaction. So we've produced 0.05 mole per liter in acetate ions. Now we substitute into this Kw over Ka, or let's just solve for X. X is equal to the hydroxide ion concentration. So solving for X right here is equal to the square root of Kw times concentration of salt, or acetate ion, over Ka. Right there. And so we save a little space, I guess. Make sure we got that right. Yeah. So now the hydroxide ion concentration is 1 times 10 to the minus 14 for the Kw value, times the 0.05 molar for the acetate ion, divided by 1.8 times 10 to the minus 5 for the Ka for acetic acid. This all comes out in moles per liter, which is 2.78 times 10 to the minus 11th molar in hydroxide ions. And as you know, POH is equal to the minus log of the hydroxide ion concentration, which is equal to minus log of the 2.78 times 10 to the minus 11 I had to rewind. I forgot to take the square root of the expression here. So taking the square root, we get 5.27 times 10 to the minus 6. Sorry about that. Anyway, POH is now minus log of the hydroxide concentration, which is minus log 5.27 now times 10 to the minus 6, which gives us 5.28 right there. So knowing that pH plus POH equals 14, we can now calculate the pH at the equivalence point of this titration, which is 14 minus 5.28, which is 8.72, and is reasonable results relative to the weak acid titration with a strong base. You can expect the pH to be in the alkaline range because the acetate ion reacts with water to regenerate, if they will, some acetic acid and leave an excess of hydroxides. It is that excess of hydroxides that pushes the pH into the alkaline range. The calculation of a strong acid titrating into a weak base is followed in the same aspect, and but you'll find that the equivalence point, the pH will be acidic, because the cation in a weak base will react with water and leave an excess of hydronium ions, which pushes the equivalence point into the acidic range. To illustrate the strong acid or weak base titration, we're just going to go straight to the equivalence point. Now, the titration sequence and the calculations are identical to the acid-base titrations we've just done. You have to still have to take the common ion into effect. In this case, the common ion would be, sorry about that. Anyway, common ion would be the ammonium ion in the titration of a weak base and strong acid. So if we look at the adding the strong acid into an ammonium hydroxide, we find that it produces NH4Cl, salt, at the equivalence point, and water right here. So if we consider NH4Cl ionizes 100% to NH4 plus Cl minus at the equivalence points, all you have, and take each one relative to its reactivity with water. We just ignore chlorine, because chlorine plus water produces theoretically hydrochloric acid. Well, that's strong acid, so therefore no reaction is the conclusion. However, the ammonium ion will react with water and produce ammonium hydroxide and an excess of hydronium ion. Well, in the case here, we've already gone to the molarities, so if you react 0.1 molar sodium ammonium hydroxide with 0.1 molar HCl, you're going to get 0.10 molar in salt, which ionizes 100% to produce 0.10 molar in ammonium ions. Well, this will turn around and react with water and produce certain quantities of ammonium hydroxide and hydronium ions, which will affect the pH at the equivalence point. So this is a K prime, Ka prime, but is still calculated in the same way as if we know what the Kb of ammonium hydroxide is. Well, Kb, I'll put that up here, Kb of ammonium hydroxide is equal 1.8 times 10 to the minus 5. You can look it up. But anyway, that equals to NH4OH, which would be that X, times the hydronium ion, which would be the other X, divided by the ammonium, or the salt concentration, right here. Okay, so Kw, we can solve for hydronium ion here real quickly. So that'd be Kw times the salt concentration right there, divided by Kb of the weak base. Getting ahead of myself. Okay, that gives you X squared over the NH4 plus, like that. And of course, X is equal to hydroxide concentration, which is the objective here. And so that is Kw times the salt concentration, or cation concentration, divided by the Kb value. There we go. And so that's 1 times 10 to the minus 14, right there. 0.10 molar for the cation concentration right here, and we have Kb value given right there. So now, actually, that's I'm getting tired. I'm sorry about that. H plus ion concentration. We're not looking for H, and so this would give us. So working through this expression, we wind up with 7.46 times 10 to the minus 6 molar in hydronium ions, and then the minus log of that will give you a 5.12. And we find that the equivalence point of a strong acid and weak base will actually be in the acidic range, because the reaction of the cation with water forms the weak base, but it also leaves an excess of hydronium ions and consequently pushes the equivalence point into an acidic range. The next time we will be getting into solubility product equilibria and see how salts dissolve, how much. Some of them don't dissolve very much, some of them dissolve quite a bit, and we'll find out how to determine the amounts that do dissolve. One of the characteristics of salts is they ionize 100%, but not all have equivalent solubilities, but whatever does dissolve will ionize 100%. So we will look at solubility product equilibrium in the next lecture.